Hey guys, welcome to your next lesson in the trigonometric functions topic. Today is an extension 1 lesson. Before we get into it, let's have a look at this flashback question. We have the value of cos theta is minus 3 on 4, and the angle theta is between 0 and pi, so it's in either quadrant 1 or quadrant 2. Using that information, find the exact value of tan 2 theta. If you think you know where to start, by all means pause the video and have a go. Okay, so in order to find tan 2 theta, we're going to need to know what tan theta is. Okay, the way we get some information about tan theta from cos theta, the easiest way to do that is to just use a triangle, a right angle triangle. Okay, here's my right angle triangle. I'm going to call this angle here theta, and for this theta to be this theta, we need cosine, which is always adjacent over hypotenuse, to be 3 over 4. Okay, so we need the adjacent side to be 3, we need the hypotenuse to be 4. We're not going to worry about the negative for now. We'll get to that later. For now, we just need the numbers. So now that we have that, we can use Pythagoras to find the unknown side length here. So we can do 4 squared minus 3 squared gives us 7. So we have square root of 7. Okay. Now that we have that, we can find the value of tan theta because tan theta is opposite over adjacent. So we get root 7 over 3. Okay. But now we have to think about whether tan theta is going to be positive or negative because we don't know where this theta is in our unit circle. So we're told that it's in quadrant 1 or 2 between 0 and 180, but cosine is negative. All right, that tells us it has to be in quadrant 2 because if we were in quadrant 1, that's where cosine would be positive. Okay, so if we're in quadrant 2, that's where sine is positive, so the other two are negative. So our value of tan theta is going to be negative root 7 over 3. Okay. The reason we need that is because to find the value of tan 2 theta, we've done this a few times, we're going to use our double angle identity for tan. So we have our tan expansion of two angles like this on your reference sheet if you're a bit rusty. We're going to change A and B both to theta and then simplify to get this. Okay, this is your identity, which hopefully a lot of you have already memorized, but if not, you can just go through that process and get there really quickly. So to find tan 2 theta, we just need to do 2 tan theta, which we just found, over 1 minus tan squared. So now it's just a bit of surd algebra. So we have the 2 times our answer before up top, and on the bottom we're just squaring it. Okay, so if we square this, we get 7 over 9, and it's positive, so we have 1 minus 7 over 9. 1 minus 7 over 9 is, of course, 2 over 9. And now we can tidy up our fractions by we can multiply top and bottom by 9, and then we can just do minus 6 divided by 2. Gets our final answer of minus 3 root 7. Okay, has to be in this form because the question asks for the exact value. Okay, so you can't just do shift cos or inverse cos of this and get a decimal. It won't be exact. You won't get the marks. Okay, so you have to do this process using your all your trig identities and all your trig knowledge. Alright, so today's lesson is focusing on further trig equations. So you studied trig equations in the advanced course. These are obviously just a little bit harder, and they use some of the extension identities that are not used in advanced. Alright, these are pretty tough questions. I'd say this is a very challenging part of the course, so take your time with this video. We are doing a few examples, so apologies, this might be a bit of a long one. Feel free to split this into 2 viewings, by all means. Okay, here's our first one. Alright, so for our first one, we are solving sine of x plus pi on 6 minus sine x minus pi on 6 equals 1 in the domain of 0 to 2 pi, so just the first lap of the unit circle. Alright, so the first way you can approach this is you can expand both of these terms here using your identity on the formula sheet of sine of a plus b. Although in the new course, there is a slightly better way of solving this by using the what's called the sums to products identities. Okay, the reason I know this is because if we compare this to the one down the bottom, we can see striking similarities. We have sine of 2 angles, A and B. They're plussing here and they're subtracting here, and we're subtracting both of those. Okay, so if you can recognize that and you can spot this identity on your reference sheet, this is going to be the best way to solve this one. Okay, we're just going to tweak this a little bit because we don't have a half out the front, as you can see. So we just need to multiply both of these by 2, and we get this. Okay, so here is how we are going to simplify the left-hand side. and make less work for ourselves and solve it really quickly, okay? We're going to write the whole thing as 2 times cos of the first angle, which is x, multiplying with sine of the second angle, which is pi on 6, okay? So we're writing it as 2 cos x sine pi on 6. So now we'll change the left-hand side of the equation to that, and we'll set it equal to 1. And now we can solve this, okay? Because now there's only one unknown term. Sine of pi on 6 is, of course, just a half, okay? Sine of 30 degrees is a half, which is very convenient because 2 times a half is just 1. So you end up with just cos x equal to 1. And then we can solve that very quickly by just thinking about the graph of cos x in 0 to 2 pi. So cos graph starts at 1 when x is 0, and it finishes at 1 when x is 2 pi. So our two solutions are 0 and 2 pi. Okay, these are the values that sub into cos and give us a value of 1, which if you forget, you can just always chuck in your calculator and double check. Okay, up to our next one. All right, so for our next one, we are solving from 0 to 2 pi, and we have 2 sec squared x plus 3 tan x minus 1 is equal to 0. Okay, so for this one, it's almost convenient because it kind of looks like a quadratic. You've got something squared, something, and then a constant. The only problem is that these two don't match. We have a tan here, and we have a sec squared here. Although, if we are clever and if we know our identities, we can actually fix this up. Okay, so all we need to know for this one is that sine squared plus cos squared equals 1. I'm assuming you know that pretty confidently by now. And what we can do is we can take the 3 terms of this identity and we can divide them all by cos squared. Okay, sine squared divided by cos squared is tan squared. Cos squared divided by cos squared is 1. And then 1 divided by cos squared we can write as sec squared. Okay, this is our identity, which should be familiar as well. And now we can substitute this into our original equation. We can change the sec squared to a tan squared plus 1. And then we'll have tan squared and we'll have tan, and we can solve the quadratic. So we substitute it in. We expand out the brackets, so we have 2 plus 2 tan squared. We can simplify by just doing the 2 minus the 1 to get a positive 1. And now we just need to solve this quadratic equation, which is a bit tough, but it's definitely doable. If you want to, you can substitute to make it look a little bit nicer. You can just let tan x equal u, and it looks a bit more straightforward. Okay, now to solve this, we can use the quadratic formula, or we can just factorize. I'm hoping if you're in Year 12 Extension 2, or Extension 1 even, you know how to factorize this. I'm not going to over-explain that. We just get 2u plus 1, and then u plus 1 equal to 0. Okay, so solving these, we end up with u equal to negative 1 here, and here we get u equal to negative a half. Although keep in mind that u is actually tan x, isn't it? Because we substituted. So we'll change those back. All right, now we're going to solve these two. Okay, this one's all right because it's a 1, which is one of the nice answers for tan. A half is not a convenient one. The good ones for tan are root 3, 1 on root 3, and 1. Okay, so we're going to get a inexact answer by just doing inverse tan. And because we have a negative value for both of these, our solutions are going to be in the second quadrant, and the fourth quadrant is where tan is negative. So keep that in mind. All right, so this one we'll do inverse tan of a half, and then we'll put our answer in quadrants 2 and 4 like this. Okay, quadrant 2, so pi minus tan inverse of a half, and quadrant 4, 2 pi minus tan inverse of a half. We can just do decimal answers for radians. We're not going to get very nice answers. That will do for today. And then for the other one, again, we're going to do inverse tan of 1, which we know is going to be pi on 4. And we're going to do those two solutions in quadrant 2 and 4. Okay, we get nice exact answers for that. We get 3/4 of pi and 7/4 of pi. So there are your 4 solutions to this problem. Okay, you got your 2 gross approximations in radians here, and you got your 2 ones here from your quadratic equation. Okay. All right, on to the next one. Okay, this one we're solving from minus pi to pi. We've got sine x cos x equal to 1 over 2 root 2. Okay, so the easiest way to go about solving this one is it's really important to know your double angle identities, okay, because they crop up quite a lot in trig equations or just trig algebra in general. And if you can spot them, it's usually really useful and it's a massive shortcut. So for this one, when I look at this, what trig is in my brain is I know that sine of 2 theta is equal to 2 sine theta cos theta, which I've written as x's to confuse you. Let's forget about that. So knowing that, when you see a sine and a cos multiplying, you can write this as just sine of double the angle, okay? We can alter this a little bit because we obviously don't have a 2 in our question, okay? We just got sine and cos, so we'll just divide both sides by 2. So now we can write this left-hand side as a half sine of 2x, not 2 theta. Very bad. All right, now that's way better because you only have one trigonometric term instead of 2, so you've instantly made the question much simpler, okay? We can multiply both sides by 2 to get rid of these pesky halves. And now we just need to solve sine 2x equal to 1 over root 2, which is a question you would get in advanced, okay? Keep in mind a good trick for this question is that because x is going from minus pi to pi, that means that 2x is going to be going from minus 2 pi to 2 pi. So make sure you make that change because otherwise you're going to miss some of the solutions. All right, so 1 over root 2 is one of our exact answers. That is the answer with sine of 45 degrees or pi on 4. So we know that 2x is going to be pi on 4. It's a positive answer, so we're going to be in the positive quadrants, which for sine are the first two, quadrant 1 and quadrant 2. Okay, so there's our first two answers. Pi on 4 and 3 pi on 4, quadrant 1, quadrant 2. Now getting the other two answers, because we're going all the way back to negative 2 pi, is pretty tricky. The way I choose to make sense of these, just personally, this is what makes sense in my brain, is I like to think about the graph, okay? Because I know there's going to be solutions in the negative lap of the circle, but I just want to be absolutely sure I know where I'm looking. So if you draw a quick sketch of sine of x, okay, your familiar graph, 0, pi, 2 pi, and it's symmetric through 0 because sine is an odd function, so it looks like this over here. Now if we're solving, whereas this function equal to 1 over root 2, here's our first solution, here's our second in quadrant 1 and quadrant 2, and now with the graph, it's really easy to see that our other two solutions are going to be 45 degrees up from 360 or negative 360, and they're going to be 45 degrees back from 180, okay? Because it's the exact same shape over here where we went 0 up and pi back. Over here, we're going minus 2 back and minus pi up, okay? So that's what works for me. That's how I know that to get the other two, I need to do minus 2 pi plus pi on 4, and I need to do minus pi on 4, okay? So that's my recommendation. So there are our other two scary negative solutions, and we get minus 7 pi on 4 and minus 5 pi on 4, okay? So the hardest part of that question, apart from the negative angles, is always a bit scary. The hardest part was just recognizing which identity to use, and that's just from knowing your stuff, really, knowing your formulas, okay? Okay, next up. Oh, and of course, pardon me, we just solved for 2x, so to finish off the question, we just need to divide everything by 2 to get values of x, of course. Okay, for the next one, we have 3 times sine x plus 4 times cos x is equal to 5. We're solving over 0 to 2 pi, so it's a nice one compared to the last one. Okay, so how are we going to solve this? If this was a sine squared or a cos squared, we could do some magic and make it quadratic, but no such luck. We have sine and cos. Okay, so the bit of content you need to be able to recognize for these questions is what we looked at in class previously, called the auxiliary angle technique. Okay, this is where we combine a sine and a cos into one trig function as either a sine or a cos. So here's how we did it. We said, well, let's look at sine of a plus b and cos of a plus b on our formula sheet and see which one of these we can make this look like. The obvious one to me is sine of a plus b because you've got a sine and a cos and they're plussing, so let's go with that. So we are hoping that there is a way of writing this left-hand side of the equation in this form. Okay, something times sine of x plus something. Okay, and it's going to work. So first thing we need to do is expand this out using our identity. So we're going to have r sine x cos alpha plus r cos x sine alpha. All right, and now if we're saying this is going to be our left-hand side here, so for these two equations or these two lines of working to match up, well, you've got a sine x with 3 and you've got a sine x with an r cos alpha. So logically that r cos alpha needs to be the 3. Okay, likewise the r sine alpha over here, which is with the cos x, needs to be the 4. So those are our two equations that we've set up now. So we're matching these up. And now we need to solve these two for r and alpha. Okay, it's a pretty straightforward way of doing this. Well, it's kind of tricky, but it's pretty straightforward. What we're going to do is we're going to square both of these. We're going to get r squared cos squared equal to 9. And we're going to get r squared sine squared equal to 16. And now we're going to add those two bad boys together. Why are we doing that? Because we can factor out the r squared and we'll get cos squared plus sine squared, which is just 1. So it's like it was never there. So writing that as 1, now the alpha is gone and we can just solve for r squared. For this one, we'll get two solutions here. We'll get 5 and minus 5. We only need one of those, so let's just take 5 because positive numbers are just better, aren't they? Less confusing for my little brain anyway. Okay, now you've got r. You can sub in and solve for alpha, or the easier option is just divide the two equations. Okay, so if we divide these two, we get 5 sine alpha divided by 5 cos alpha. And of course, sine alpha divided by cos alpha is tan alpha. All right, so now we can solve this equation by just taking inverse tan of 4 on 3, which again is not a very nice exact answer, but it's an answer nonetheless. It's about 0.93 radians. Okay, this is good news because now we can take this left-hand side of the equation, which was the scary part, and we can instead write it as r sine x plus alpha, where r is 5 and alpha is 0.93. Okay, the reason that's better is because once again we've gone from 2 pieces of trigonometry to 1, which is going to be easier to handle in terms of algebra. Okay, so solving this, we can divide both sides by 5. All right, now so for solving this, we're going to think about where is the so we have sine of something equal to 1. So we're going to think about the graph of sine x from 0 to 2 pi. Okay, the only place the graph gets up to its maximum amplitude of 1 is at 90 degrees, so pi on 2 radians. So we've got x plus 0.93 radians is pi on 2 radians. So subtract the 0.93 and we have solved for x. Works out to be roughly 0.64 radians. Okay, there's your answer. So whenever you see a sine x and a cos x plussing together and you're asked to solve, this method, which again is called the auxiliary angle technique, is super useful. Okay, next one. This is from the 2008 HSC paper. We are going to show that for all values of theta, sine of 3 theta is equal to 3 sine theta minus 4 sine cubed theta. All right, and using that information, we are going to solve the equation in part B. So first thing is the identity. So my class has done a few of these before. The way we write sine of 3 theta in this form is we use our double angle properties, and we're going to write sine 3 theta as sine of theta plus 2 theta. Okay, this guy here. So we're using the double angle formula on the reference sheet, writing 3 theta as 2 theta plus theta, and doing our expansion. So we got sine of 2 theta, cos of theta, sine of theta, cos of 2 theta. Okay, so now notice that our answer needs to be all in terms of theta. We don't want any 2 thetas, so we've got to fix these two guys here. Sine of 2 theta, as we looked at before, can be written as 2 sine theta cos theta. Cos 2 theta is a bit tricky because there's 3 different ways of writing this guy. The one we're going to want is only involving sine squareds. So we could have written cos 2 theta as cos squared minus sine squared, but instead we're going to write it as 1 minus 2 sine squared. Okay, so there are our identities. Now we've got 2 sine theta cos squared here if we multiply, and here if we expand we get sine theta minus 2 sine cubed. So So almost there, we've got everything except this cos squared needs to be something else because there's no coses in our answer. So we're going to use the fact that cos squared is just equal to 1 minus sine squared by rearranging the Pythagorean identity. So we have 2 sine theta times 1 minus sine squared. We'll expand this out, and if we tidy it all up, because we get 2 sine theta minus 2 sine cubed, tidying that all up, we get the target as required. So we write QED, in your face, we are the smartest. Okay, cool. So now that you've seen that, now that we have another way of writing sine 3 theta, let's see how we can use it in the next part. So we are solving, let's go back to the question, pardon me. We are solving sine 3 theta plus sine 2 theta is equal to sine theta. All right, we're going to use the fact that in part 1, we showed that sine 3 theta can be written in this form here. So we're going to substitute that into our equation. Okay, we're changing the sine 3 theta to this one here. Okay, up next, we're going to bring this sine theta across. So we're going to have only 2 sine theta now. And what we're going to do is we are going to factorize, okay, because we have 3 terms here. And what's common is there's a 2 sine theta in all of them. So we'll factor this out, and now we have 2 equations to solve. All right, the first one is sine theta equal to 0, which we can solve by, again, thinking about the graph of sine theta. And inside we have a quadratic, almost a quadratic, sorry. We have minus 2 sine squared plus cos theta plus 1 equal to 0. This is kind of like the second example because it's looking like it wants to be a quadratic, but it's not quite there. But we can help it along by rearranging and using the fact that sine squared is equal to 1 minus cos squared. So this is the different form of the equation we did before, and it's a kind of a common trick in HSC papers for a upper level question for trig equations. So we'll write sine squared theta as 1 minus cos squared. We'll expand that out and we'll collect up what we can. And we end up with this 2 cos squared plus cos minus 1. So now we will solve these 2 equations. We can factorize the quadratic. Again, I'm going to assume you know how to do that. You can write these as u squareds and u if you feel more comfortable, or if you can just go straight to it, I encourage you to do so. But there is our factored form. And now we're going to get our 3 equations solving equal to 0. So we're going to get the first one, sine theta equal to 0. We've got the middle one is going to have to be cos theta equal to 1/2, and the one on the end is going to be cos theta equal to -1. So for our sine theta equal to 0, again, thinking about the graph and where sine theta cuts the x-axis in the from 0 to 2 pi, we have 0, pi, and 2 pi. Okay, 0, pi, 2 pi. If we're solving cos theta equals 1/2, we know that cos of 60 degrees, or pi on 3, gives us 1/2. And because that's positive, we'll have to do quadrants 1 and 4. So we're going to add on the first quadrant, pi on 3, and the fourth quadrant, which is 5 pi on 3. And for the last one, cos theta equal to -1, again, we'll think about the graph. So thinking about the graph of cos starting at 1 and finishing at 1, the only place it is -1 is in the middle, which is pi, which we already have. So there you go. All right, so writing those in the proper order, we have 0, pi on 3, pi, which we had twice. So there you go, very special. 5 pi on 3, and 2 pi as your 5 solutions to the original equation. So yeah, definitely a very difficult question. Quite a lot of tricks in there that hopefully you are now at least more aware of. All right, last one, guys. We are finding all the solutions for this equation, cos theta equal to √3 on 2. All right. The reason this question is so different to the 5 we've just done is in the 5 before that, I told you some domain of x or theta, which I wanted you to solve over. In this question, I've just said, find all the solutions, which is a bit of a weird question because you guys know that this equation has infinite solutions, okay? Because it just keeps going round and round the unit circle forever. So what we're going to do is we're going to use our brain, our intellect, and a bit of luck to find a way of representing all the possible solutions. Okay, this is called finding the general solution of a trig equation. So let's just get some solutions for this equation. and see if we can sort of form a pattern that we can represent using algebra. Okay, so cos theta equal to root 3 on 2. We know that cos of 30 degrees, or pi on 6, gives us root 3 on 2. And a positive answer tells us we're in quadrants 1 and 4, okay, for cosine. So here's our first two. We're going to do these in degrees to start off because I think it's a bit easier to see, and then we'll convert to radians at the end to be fancy. So here's the first two, and the way we get the next two solutions, well, you just do another lap around the circle. So 30 degrees, and if you do another lap, so you add on 360, you get 390. Okay, and 330, if you do another lap, you add on 360. So what we're going to see is that all our solutions are going to be right here and right here, 30 degrees up and 30 degrees down from the 0 to pi line. Okay, 30, 330, 390, so on and so on. Okay, so how can we write this in an algebraic form that's going to make sense? Well, I guess you could say that all of our solutions are going to be within 30 degrees up or 30 degrees down from 2 pi. Okay, so they're always 30 degrees above 2 pi or 30 degrees below 2 pi, where we're just doing lots of multiples of 2 pi. 1 lap, 2 lap, 3 lap, forever. Okay, that's the pattern we're going to try and write down now. So we have 0 plus or minus 30, because remember we can have negative solutions for this because we can have solutions from 0 to positive infinity or 0 to negative infinity because we're finding all of them, which is really daunting. So we can have 0 plus or minus 30, we can have 360 plus or minus 30, 720 plus or minus 30. We can go back the other way and do negative 360 plus or minus 30. What I'm trying to show you here is that all of our solutions, if we kept on listing them, they would always be a multiple of 360 plus or minus 30 degrees. And here's how we write it. Okay, we have, our answer is always going to be a multiple of 2 pi, whether that's 0 or 1 or 2 or however many laps you want, plus or minus pi on 6. Okay, so this is what's called the general solution for cosine. Okay, so it's just 2 pi n plus or minus your first solution, which in this case, because it's root 3 on 2, was pi on 6. Okay, so these used to be on the reference sheet and they used to be assessed quite frequently. These formulas have recently been taken off the reference sheet, but there's still some debate as to whether these concepts will still get assessed. My guess is probably not, but I thought I would show you this just to be safe, so that if you do see it, you are vaguely familiar and we can do some more practice later if we need to. All right, well done if you made it to the end of that. I'm exhausted, I'm sure you are too. You can have some more practice and try some by yourself in exercise 405. There's heaps in there, and as I said, these are very difficult, so be patient, and if you get stuck and you want some help, as always, please let me know. Okay, thank you so much for watching. I hope that helped in some way. I hope you're still awake. Thanks guys, see you later.